Hello, my name is Elena, and I'm a Moore's-Law faculty fellow in NYU. In this presentation, I would like to introduce my work on comparing visual understanding as performed by humans and deep neural networks. Computational modeling of the human visual recognition system allows better understanding of how the system is designed in humans. This understanding can potentially help with visual deficits and diseases such as dyslexia. We first investigate reading as defined as recovering the sequence of letters from an image of a word. We also study a simple classification task. I'll begin with a model. In computer vision research, the class of problems that aim to translate visual images of text into corresponding letters is known collectively as scene text recognition. We use a popular model, a convolutional recurrent neural network, as our computational model of reading. The model receives the image as an input, resizes it to an image of 32 by 100 pixels, and extracts a set of features using a convolutional neural network encoder. Then it processes the features using a recurrent neural network trained with connectionist temporal classification laws to output a sequence of letters. Next, we looked at three known phenomena of the human visual processing pipeline and investigate if the neural network model exhibits similar patterns. We focus on crowding, the inability to recognize a target that is surrounded by clutter, efficiency, the performance when presented with noisy input, and speed accuracy trade-off, performance when presented with a limited computational budget. First, we look at the phenomenon of crowding. Looking directly at the A, it's easy to recognize it, and it remains so when you put your eye on the nearby green plus. However, if you place your eye on the red minus, which puts the A in your periphery, then the A is crowded, and you see only a jumble of black sticks. Take a few moments to look at the demo. Human vision is worse peripherally with worse crowding. We thought that the pooling in our model might be a similar research limitation. We compared human data from several eccentricities, more and more peripheral, with network data with several sizes of pooling from 2 to 32. In the network, regardless of pooling value, we found only one slope, a negative 0.3. While in the human results, there are two regimes, one limited by crowding and another limited by acuity. Therefore, the network that we investigated did not exhibit crowding. Next, we looked at efficiency, or the inability of both the human observer and the computational model to withstand noise in the input. Efficiency is defined as the fraction of the word's contrast energy, the product of the word area and the square of contrast that would be required by the ideal mathematical classifier. You can test your own efficiency relative to the ideal word classifier by reading down the chart as far as you can. Each line has a lower contrast. The noise is fixed. The green arrow indicates the average human threshold. The blue arrow indicates the average human threshold for 75% correctness. The green arrow shows the threshold we found for our first computational model, much worse than the human. We find that the model needs 3 times more contrast than the human to achieve 75% correct. This rejects our computational model as an account for human behavior. Many works today often recognize objects as well as people do, and thus might serve as models of human recognition process. However, most such networks provide their answer after a fixed computational effort, whereas human reaction time varies from 0.2 to 10 seconds, depending on the properties of the stimulus and task. In this test, we looked at the ability of the neural network to produce a classification result when presented with a noisy input. To model the effect of difficulty on human reaction time, we considered a classification network that uses early exit classifiers to make anytime predictions, comparing human and MSDNet accuracy in classifying CFAR10 images in added Gaussian noise. When the network is trained with an appropriate noise model, the network is more efficient, therefore it can tolerate noise much better. When appropriate amounts of noise are present to bring the two observers, the human and the network, into the same accuracy range, they show a very similar dependence on duration or flops, i.e. they have a similar speed accuracy trade-off. These experiments document important differences, but also similarities between visual processing performed by neural networks and by humans. In particular, we found that the studied network model did not exhibit crowding and had much lower efficiency and tolerance to noise when these conditions are not present during training. However, the network was able to reproduce a speed accuracy trade-off. In the future, we will investigate the performance of other neural network models and check their similarities between human visual processing system and neural network computational models. Thank you.